Welcome everyone at session 9. In this session, we'll learn about gradient descent variants. Or actually backpropagation invariants. We have learned it in the first or the third lecture, the third and fourth lecture. We have learned about the main or actually the core backpropagation algorithm, the core gradient descent, which is equal to weight, for example, at time t plus 1 is equal to weight at time t minus the learning rate multiplied by the gradient. So these are the core gradient descent function or model. But there were many adoption of this model to increase the speed of learning, to avoid explosion and vanishing, and also to deal with big data. For example, if we have really big data, that means we cannot do the optimization on this big data at every iteration, as we'll see in the next examples. So that's why we get now new, actually, let's say every year we get a new variant of gradient descent. One of the things also they care about the learning rate. We have talked about this, that if you have a large learning rate, you might keep oscillating and miss the global minima or local minima. But if you have a small learning rate, it might take, for example, too long time to train the network. So this basically why we get always new publications and research about improving the gradient descent and improving the optimizers in gradient descent. So I'll talk now about the stochastic gradient descent, which is very common, especially when we deal with big data, as I said. So now recently, or actually, let's say starting from 10 years ago, most of the successful neural networks that actually they have really good performance and good real case scenarios, they consist of at least 1 million weights or parameters, which is a lot of weights within this neural network. So this we have 1 million parameter, but also we have now big data. We have training sets, for example, that consists of 1 million rows or 100 million rows, like 100 million images, for example, we can get. So considering these two, let's say, dimensions, which is the number of weights and also the number of samples. So these two facts, that means that we need, for example, if we're talking about 1 million, we need about 10 to the power to 12 terms actually at each gradient descent step. So there's a lot of gradient descent steps, because if you look at the backpropagation, the first step is feed forward, right? Where we need to feed the network with all our training data, which means we need to feed the network with 1 million here, 1 million samples. And then at the end, we need to estimate the cost of this 1 million samples. And then we need to update 1 million parameters with this 1 million samples. So it is basically here we have 1 million and 1 million. That's why we have 10 to the power 12. So we have about 12 basically zero there, and 12 zeros terms to at each gradient descent. So there is no computing device can handle that number of operation. So this is the idea of gradient descent then, is to use what is called mini batch training. The idea of mini batch training that at each iteration we don't take the whole data set, but we take mini batch. This mini batch could be single sample, but could also be bigger than that. Usually it has the value of 2 to the power of n, and this n could be 1, 2, 3, 4, whatever, which end up basically in 1, 16, 32, 64, or 128 samples for each mini batch. So the idea here, for example, at each iteration, we take the first 16 batch of the or samples of these from our training set. We do the backpropagation. Then we move the next 16. We do the backpropagation, next 16, and so on until we finish from our data set. then we repeat that again, and this is basically we do keep doing that until of course we reach the minima. Now this also has a kind of first of all, it's better in terms of finding global minima versus local minima, because we don't have a look at the whole cost function always, let's say, at the same time. What we are seeing, or what the gradient descent is seeing, part of the cost function at each iteration, and that basically, because it sees only the part of the cost function, what is happening with the gradient descent is doing a lot of oscillation until it reaches the global minimum. While if we have the whole data set at once, it will go straight to the local or global minimum. But as I said, we cannot have that because of we cannot deal with big data, and we need to have stochastic like here. This oscillation, because of this oscillation, we might actually find more global minima than the local minima. Let's say we have here a global minima, and this is the local minima, and we started here. Then if we don't have here stochastic, it will go directly and it will miss, for example, here the global minima. And in stochastic, because it's doing this oscillation, at one step it might find, okay, I found here better than what I was going to or was tending to go to, then it will change its direction to the global minimum. So because of this oscillation, the model or the gradient descent is exploring the space more, because here it actually doesn't do any oscillation, it goes directly to the what it sees from the beginning. But here, because of oscillation, it explores more, and the chance of finding global minima is higher. So it is called stochastic also because of that. It's basically doing a lot of oscillation. It doesn't see the whole cost function from the beginning, at once from the beginning. Now, this stochastic gradient descent is what actually used now. We don't have gradient descent because, as I said, we have big data. We cannot load the big data at once to our optimizer. We usually do mini batch training, and you will see 16, 32, 64. The reason we have 2 to the power of n basically because of our GPUs, or graphical processing unit. Their memory and the way basically the dataset would be divided or split it and distributed over this memory. The memory of basically the GPU is also divided in this way, to the power of n. And what would happen basically is this 16 would go to one of the let's say cores of that GPU, another 16 would go to the other core, and this way we can parallelize the processing. It's always in your network, because we are dealing with GPU, it's always to look at this basically formula or this notation here, to not only choose the number of, or the size of the mini patch, but also to choose the number of neurons. For example, it's a good practice also if we are choosing number of neurons in your network to have it, let's say, from to the power to the power of n, let's say 16, 64, 128, and or 1024, and so on. Number of iterations, number of hidden layers, number of or the number of samples per mini batch. We talked about gradient descent or stochastic gradient descent. And now we have another variant of gradient descent, which is stochastic gradient descent with momentum. Why momentum is important? So I said oscillation is important because it makes finding global minima easier. But also too many oscillations is not that good. In physics, too many oscillation could lead to instability, but also here in learning, it could make learning much slower. And that's what we don't want actually. So the idea of momentum is to make basically the training faster and also to avoid instability in the system. Momentum is in physics basically it's kind of act like a damping factor, and when we talk about statistic, momentum is like exponential moving average over a signal. What the meaning of that? Let's say we have here a temperature and days signal. So these are days, and the blue one is temperature. We can see we have a lot of oscillation if we look at the real data, which is the blue one. Usually, one of the models that are used to do predictions in statistics is the moving average model or the exponential moving average model, which is here the red one. It still oscillates, but it basically has a lower frequency than the original one. It still represents the trend of the blue one with much less oscillation, as I said. If we have here such let's say uh, cost function like this one, which is asymmetric and it's kind of squeezed, which means here if we start from there, the model would do a lot of oscillations along the y-axis here, and basically it should actually don't do this oscillation and should go directly in the direction of x, or actually it needs to reduce oscillations, for example. The idea of doing, or so actually how we can do that with the gradient is similar as the exponential moving average. We need to apply the exponential moving average over the gradient signal. And to do that, so this is our gradient descent, adopted gradient descent now. Originally we had here wk plus 1, k here is the index of the iteration, plus 1 is equal to wk, and minus the learning rate alpha. Usually here we had the gradient or the first derivative of the cost. Now instead of that we have the momentum, and the momentum is actually equal, it has another formula here. So the momentum at time k plus 1 is equal to the beta, which is here a factor that we multiplied by the previous sk. Here we are like now calculating the speed of that basically signal, like for example the speed of the red light, or actually we're talking now about the average, moving average as well. So here we have sk plus 1 minus beta multiplied by the gradients that we usually use. So usually we had here the gradient in this place. Now we have it here. We are, instead of applying the original gradient signal, which is here in the blue, we are applying the smooth one, which is in red, which is actually the momentum signal. In this way, we avoid too many oscillations. We still have basically the trend, we still have the direction that this gradient should take, but with less oscillation and more stability. And if you hear about gradient descent with momentum, this is basically what it does. It replaces the gradient with this formula, which is actually representing the exponential moving average. So what is the value of beta here? The most common one is 0.9 that is used. And here there are some simulations, for example, that you can see online. You can see here basically many oscillation, and there's this, and also a lot of discussions about the momentum. It's very interesting if you want to look at it. But here we see three examples of the alpha or the momentum, beta or the momentum value. Starting from equal to 1, which is under damping, which means here we are not damping the oscillation at all. And this is basically its oscillation in 2D, where we have, let's say, two weights here. And we can see it would basically do a lot of oscillation until it reaches the minima, which is here, or the global optimum here, or reach the optimum. If we have a critical damping, it would reach eventually the minima, and here basically it would do not really a lot of it's one oscillation only from the beginning to the end. So there are no oscillation at all, or actually one oscillation actually from the beginning to the end, and this is basically called critical damping. So from the beginning to the end, it would like only one oscillation, or one, let's say, direction from the beginning to the end. Oversampling means that we really oversample this signal. It won't reach the minima at all. It's like we actually overdumped. As I said, the momentum is acting as a damping factor. So when we overdump, means that we overdump the oscillation, we overdump the speed of this gradient here, and it would stop before reaching the global minima. Here in underdamping, it is possible that it won't reach the global minima because it's keep oscillating, as I said, which is not that good, because here we won't reach the global minima and we won't get stable gradient at the end. So the optimum one, as I said, is between the under damping and critical damping, which is usually 0.9, where we have some oscillations, because as I said, oscillations are good, but not under damping, which means not too many oscillations that makes the system unstable, but also not critical damping, which is very low oscillations or no oscillation at all, which basically makes it probably avoid global minima and converge at local minima. Another technique is called RMS prop, which is, if you think about it, the momentum is about moving average. RMS prop, which is from root mean square, basically signal here, which is usually represent the variance. So here we have moving variance of the signal. So there is moving average, here moving variance. It's also used for the same purpose, is to decrease the oscillations, mainly along this axis, for example, where we have too many oscillations, and to speed the model in direction of the W in this case. So it's as I said, it's like the moving average, but here moving variance. That's why the signal is, or the value or the model here, similar. This part is the same until here, but here we multiply by the square of the W, or the gradient there. And here, instead of having SK, we are kind of normalizing the gradient with respect to the variance. So this kind of represents the moving variance, as I said. And here we are dividing by variance to have a kind of unit variance for that oscillation. So we are trying basically to normalize that, let's say, gradients here by dividing over the standard deviation. So when we have here square, this is the variance, and here we are doing the standard deviation. We have seen that in the normalization or the standardization of input features on your network. We said we have the Z-score standardization, where we divide it by the variance by the standard deviation of the model. We are doing that here the same. So it is similar to momentum, but here we use the variance instead of the mean or the moving average. Okay, so we are trying to remove the variance. Actually, we have a unit variance there, because also variance means oscillations, too many oscillations around the mean. Now Adam here is a very famous technique in gradient descent. Simply, it's a combination of, I'm sure you thought about it, why we don't combine then the mean and the variance. It is basically a combination of momentum and RMS prop. And the idea here is, so we have the two formulas, one for the RMS prop, and this one for basically the momentum. And then the formula would be basically, instead of dividing the gradient by the here the standard deviation, or the variance with a square which leads to standard deviation, we take the mean. So we are taking the mean over the standard deviation, and this would be actually the signal that we use to update. Adam is one of the really common technique. It's one of the best gradient descent optimizer. There is a new one, it's called REDAM, which is rectified Adam. If you want, you can have a look at it. It's also now becoming very popular because it makes training much faster. All these techniques, as I said, the goal of them to make the training faster, to avoid local minima, and avoid explosions or vanishing of gradients. Thank you.